All right, ready to dive in. We've got some seriously cool CO2 absorption tech to unpack today.
Definitely. And you've sent over a paper that really tackles, the big one, CO2 emissions, how to capture them.
Yeah, this research paper really caught our eye.
It's called, let me get this right, effective stretching ratio on the structure and enactment of porous PVDF-HFP hollow fiber membranes for CO2 absorption.
Quite the mouthful.
It is, but super relevant and just came out November 29th, 2024. So we're talking brand new stuff here.
Hot off the presses. And the focus is on these, get this, tiny tubes.
Hollow fiber membranes.
Yeah, and they're stretching these things during production to make them even better at grabbing CO2.
It's all about maximizing surface area. Like if you poke more holes in a sponge, you can soak up more water, right?
More surface area.
Same principle here. These hollow fibers, they're made from this material, PVDF-HFP, and stretching them creates more of those holes, essentially, or pores, technically. So more places for the CO2 to get trapped.
So just by, pulling on these tubes faster, they can change how well they work. That's what this stretching technique is all about.
Yeah, exactly. It's pretty fascinating how much of a difference it makes.
But stepping back for a sec, why is capturing CO2 such a big deal? I mean, we all know it's a problem, but...
Right. It's not exactly breaking news, but it is the problem to solve. This research is, part of this huge global effort going back decades to tackle climate change.
We're talking Kyoto Protocol, Paris Agreement, all that.
Exactly. It's not just agreements. It's about solutions that work.
Yeah.
And CO2, as a greenhouse gas, if there's too much of it, it traps heat. And that leads to, everything we're seeing with global warming.
Yeah, no escaping that. So where do these membrane contactors fit into all this? Are they the solution?
They're a really promising one. They're neat because they combine liquid absorption and membrane separation all in one device.
So it's more efficient?
Way more efficient. It's basically a thin wall. One side's exposed to the air with the CO2. The other side has this liquid that loves to absorb CO2. So the CO2 goes through the membrane, gets grabbed by the liquid, and poof, gone from the air.
Clever. Okay, so we've got our CO2 problem and a potential solution. Now, tell me more about this PVDF-HFP. What makes it so special for CO2 capture?
It's got a bunch of great properties. First, it's hydrophobic, meaning it hates water.
It's water resistant.
Even better, repels it completely. That's huge, because if the membrane got soggy, it wouldn't work as well. Plus, PVDF-HFP dissolves in certain solvents, so it's easy to work with. Shake it into those hollow fibers. And it can form what we call asymmetric membranes.
Asymmetric membranes. Okay, now you're just showing off.
No, think of it like a filter, but high-tech. It's got layers, and either layer helps snag those CO2 molecules.
Ah, a super efficient CO2 trap, but tiny. And this research, they're focusing on how stretching these membranes during production can make them even better. How do they even make these things in the first place? What's this stretching technique all about?
Right. So they use this method. It's called non-solvent-induced phase separation, NEPS for short.
NEPS, got it.
Basically, they dissolve the PVDF-HFP in a solvent, then they squeeze it, like toothpaste, through this tiny thing called a spinneret into another liquid that makes it solidify. That's how you get the hollow fiber shape.
Okay, so we got tubes. Now, where does the stretching come in?
During that squeezing process, they can change how fast the fibers are pulled, and that creates the stretching force. Imagine pulling taffy. They call this the stretching ratio, or SR. And figure out the best SR. That's what this research is all about.
So they're fine-tuning it by how hard they pull, makes sense? But how do they even see what's going on inside these tiny tubes? I mean, we're talking microscopic levels here.
They use a super powerful microscope, a field emission scanning electron microscope, or FESM.
Catchy name.
It can zoom in millions of times. And what they saw in these hollow fibers is pretty amazing.
Okay, I'm intrigued. What does a CO2 capturing membrane look like up close?
It's imagine tiny tubes with finger-like projections sticking out, and inside it's kind of sponge-like. All that's to maximize surface area so more CO2 gets trapped. Like a tiny jungle gym for those CO2 molecules.
So much complexity all in a tiny tube. And it sounds like stretching them just right is key. What did the researchers find when they experimented with different stretching ratios?
Well, here's the thing. Stretching does increase CO2 permeance, which is how easily the CO2 goes through the membrane.
Okay, so good so far.
But too much stretching, the membrane gets weak. Too little, and you're not getting the full benefit.
The Goldilocks problem. Got to find that sweet spot.
Exactly. They found that the best ratio, the magic number, was 1.5. That gave the best pore size for CO2 capture, the best permanence, and the best mass transfer resistance.
1.5. Got it. But this all sounds pretty delicate. How well do these stretched membranes actually hold up over time? That's got to be important, right?
Absolutely. Durability is key.
Especially if they're going to be used, constantly.
And that's what's great. The optimized membrane is really stable for a long time, like 80 hours of continuous use, and the CO2 absorption only went down by 9%.
Wait, so they ran these things nonstop for like 3 days straight, and only a 9% drop? That's impressive.
Right, especially when you compare it to other PVDF-HFP membranes. Some of those had drops of like 27%.
Okay, so stretching seems to be working, but what about the cost of all this? Is it more expensive to stretch these things than just using regular membranes?
That's the best part. Tweaking the stretching ratio is a simple, cheap way to make them better. You don't need any fancy modifications or expensive additives.
So better A&D cheaper. That's a win-win. But before we get too excited, let's get into the nitty-gritty. Where does the actual CO2 absorption happen? How does this all work in practice?
That's a great question, and that's where we'll pick up in part 2 of our deep dive. We'll explore the heart of the action, the gas-liquid membrane contactor system. Stick around, it gets even more interesting. Welcome back. So last time, we were talking about these super stretched membranes and how they can really grab that CO2.
Yeah, it's pretty amazing how a little stretching can make such a difference. But where do these membranes actually do their work? It can't just be like floating around.
Right, they need a place to do their thing, and that's where the gas-liquid membrane contactor comes in.
Ooh, fancy name. What is that? Some kind of high-tech contraption?
It's actually pretty straightforward. Think of a bunch of those hollow fibers we talked about all bundled up inside a stainless steel tube, like a container, but for CO2 capture.
Okay, so we've got our membrane bundle. What happens next?
On one side, we introduce the gas that has all the CO2. Could be exhaust from a power plant or even straight from the air. This goes inside the hollow fiber.
And on the other side.
That's where the liquid comes in. There's a liquid absorbent flowing on the outside of the fibers. In this research, they used just plain water.
Just water.
Yeah, simple. And remember, PVDF-HFP is hydrophobic, so the water doesn't soak into the membrane, it just flows past it.
Got it. So we got the CO2 on one side, water on the other, and our super membrane in the middle. How does the CO2 actually get captured?
It's all about concentration. You see, there's way more CO2 in that feed gas than in the water. So naturally, the CO2 wants to move to where there's less of it.
And our stretched membrane helps it do that.
Exactly. The CO2 goes through those tiny pores in the membrane and gets absorbed by the water. And remember that magic stretching ratio of 1.5, that basically makes it even easier for the CO2 to pass through.
So it's all about making the pathway as smooth as possible. But why just water? Wouldn't something, I don't know, stronger grab even more CO2?
That's a great question. And yeah, you can definitely use different liquid absorbents. For industrial applications, they often use amines, which are chemicals that really love CO2.
So it's customizable, depending on what you're trying to achieve. But this research stuck with water. What did they find?
They measured something called CO2 absorption flux. Basically, how much CO2 is being captured per unit area of the membrane over time.
So higher flux means more CO2 captured.
You got it. And they found that as the water velocity increased, so did the CO2 absorption flux. Basically, fresh water with less CO2 is constantly being supplied, so more CO2 can keep moving across the membrane.
Like a constant refresh button, keeping things moving.
Exactly. And of course, the membrane with the 1.5 stretching ratio, that performed the best, even at lower water velocities.
So far, so good. But what about long-term performance? What happened to that CO2 absorption flux over time?
Well, they ran these membranes for a whopping 80 hours straight.
80 hours? That's like a marathon for a membrane.
It is. And both membranes, they had a little bit of a flux decline in the beginning. Maybe some water vapor got trapped, even though they're hydrophobic.
So even with the water-repelling properties, a little bit still snuck in.
Happens. But here's the important part. The pristine membrane, its flux went down by 27%, but the stretched one, only 9%. And then for both of them, the flux was stable for the rest of the 80 hours.
Wow, so the stretched membrane really held its own. But how does that compare to other research out there? Are there even better PVDF-HFP membranes?
Now, this is where it gets interesting. They compared the results to other studies, and get this, even with plain water, their stretched membrane performed just as well as some membranes with, like, special chemical modifications or expensive additives.
So they got similar results, but with a simpler, cheaper method. That's pretty remarkable.
It is. It means we might not need all those complicated, expensive modifications. Just optimizing the structure with stretching could be enough to get really good performance.
This is starting to feel like a real breakthrough, but what does it all really mean? What are the implications of this research for, the big picture?
That's the perfect question to lead us into part 3. We'll explore what this research could mean for the future of CO2 capture technology. And it's pretty exciting stuff. Stay tuned.
All right, we've really gotten into the nitty-gritty of how these stretched membranes work, but let's zoom out for a second. Big picture time. What does this research actually mean for the future of CO2 capture?
It's a good question, and I think what's exciting is that it hints at CO2 capture tech becoming more accessible, more efficient, cheaper, more widespread.
So it's not just about cleaning up the mess we've already made, but preventing more of it in the first place.
Exactly. Imagine integrating these things, these tiny tubes, into industrial processes, power plants,
Yeah.
maybe even systems that just pull CO2 straight out of the air.
Like turning CO2 from a villain into something useful? Is that what people are talking about when they say circular economy?
Yeah, you got it. It's not just capture, it's using what you capture. There are already companies turning CO2 into fuel, building materials, even plastics.
So we're not just solving a problem, we're creating opportunities. That's pretty cool. But being realistic, this research is just one piece of the puzzle, right? What are the challenges? How do we actually scale this up?
Well, yeah, scaling up any technology is tough. We need to know these membranes can handle real-world conditions. Think about that flux decline, even with pure water.
Right. Just a bit of moisture causes a dip.
Now imagine a factory, right? Heat, maybe corrosive stuff in the air, all sorts of things that could affect those membranes.
That could be tough.
And then, even if the membrane itself is fine, you got to think about the whole system. The flow rates, the packing density, how much energy it all uses. It's complicated,
A lot of moving parts.
but the potential is huge E. This research is a great starting point.
It definitely gives us a lot to think about. And, it makes me wonder, could this stretching technique work for other types of membranes? Aren't membranes used in a lot of different things?
Oh yeah, for sure. Water purification, gas separation, even some medical stuff.
So could this be a breakthrough, not just for CO2, but for all sorts of things? A stretching revolution in membrane tech?
Who knows? That's the fun part of science. Sometimes the simplest things, like just stretching something, can unlock all these possibilities.
It's a good reminder to keep our eyes open. The next big discovery could be hiding in plain sight, just waiting for someone to stretch their imagination. And on that note, that's all the time we have for this deep dive. Thanks for joining us.